Hello, welcome back to Advanced Quantum Mechanics. This is lecture 22. So we covered the Heisenberg picture. This was how we started with quantum mechanics. Here is a quick summary, Heisenberg picture. In the Heisenberg picture, we calculate the predictions for the expectation values of some arbitrary observables in this way. We have the initial state vector psi, and then we have time-dependent observables. Just like in classical mechanics, the observables are time-dependent. Also in quantum mechanics, they are. And this is, of course, equal to this expression here using the time evolution operator. U hat of t and psi, right? And what do we effectively do when we work with the Heisenberg picture is that we bracket in this way. Because then this is a time-dependent operator f hat of t. Now we know what the equations of motion are in this case. Equations of motion are I h bar and then f hat dot of t equal to commutator of f hat of t Hamiltonian of t, and psi is constant. It's the initial state vector. Now in contrast, the Schrodinger picture looks like this. In the Schrodinger picture, we calculate the predictions in this way by taking the time-dependent Schrodinger states and have the operators frozen in time. And let me write this out as well. So this is, of course, equal to, again, psi, u hat dagger of t, f hat of t naught, u hat of t, psi. And when we work in the Schrodinger picture, our choice of bracketing is this way. Because this is the Schrodinger state. So this is psi of t. Well, actually, this is the other way around. Here we have this, and here this one is psi of t. In this case, the operator is frozen, but the state is evolving in time. And the equation of motion in the Schrodinger picture is the Schrodinger equation, I h bar d by dt, psi of t equal to h hat Schrodinger of t, psi of t. Now, sometimes it is useful to employ a different picture, not the Schrodinger picture, not the Heisenberg picture. And that is the so-called Dirac picture, often useful. is the Dirac picture. Now the Dirac picture, the way we will cover it now, will appear perhaps a little bit more complicated than the Schrodinger or the Heisenberg picture, but there's a good reason to use the Dirac picture. And that's when we are dealing with really difficult problems. Then the Dirac picture is usually used. In fact, most of the time, in most of my calculations, almost daily, I use the Dirac picture. It is, by the way, also called the interaction picture. Also called the interaction picture. But is it useful? What's the idea here? Well, the idea is to handle particularly difficult problems by splitting them into an easy and a hard part. So assume the case where the Hamiltonian, let's say the Schrodinger Hamiltonian, remember the Schrodinger Hamiltonian has its operators frozen in time at the initial time. Let's assume we are dealing with a quantum mechanical problem where the Hamiltonian can be split into two pieces where we split such that the first term is what may be called an easy to handle term. And the second term is the one that is difficult to work with. So this means this is the easy term. And this one is trouble. So we actually often run into problems like this, where in principle we can solve the problem at hand, but there is an extra term that messes everything up and we can't solve it anymore, or at least not easily. Here are examples. Let's say the Schrodinger Hamiltonian is p hat squared over 2m plus m omega squared half x hat squared. So far it's just a harmonic oscillator, but then we also have a term plus alpha x hat to the fourth. Now that makes it difficult. But you see, the idea now is to say, this part we know how to handle. Let us call this part the easy part of the Hamiltonian, and this one is the difficult part. So this is this one. This is that one. Okay, so that would be a natural way to identify an easy part and a difficult part. See, if it was only for this piece, we would know how to solve everything. Another example is this. Let's say we have a Schrodinger Hamiltonian, which is of the form p1 hat squared over 2m plus p2 hat squared over 2m2, let's say, and 2m1. So this would be, let's say, two free particles in one dimension. And then we have plus some number gamma, and then x hat 1, x hat 2, and p hat 1, p hat 2, plus p hat 2, p hat 1, x hat 2, x hat 1. That's a self-adjoint part, but it makes things complicated. It means that these guys start interacting with each other, will interact with each other. And again, we would say, all right, this is then an h hat easy of t. Actually, there's no particular time dependence in this yet. And that thing we would call the h hat difficult of t. Just wanted to show you an example like this to indicate that often it is the term that describes interactions, in this case between two free particles, that makes life difficult. And that's why the Dirac picture is also called the interaction picture. We almost always use the Dirac picture when calculating the interaction between two systems. So now the overall idea here is, Dirac's idea was this. Let's try to use knowledge of solution to the h hat e s of t system. Right? So if the system had only that part, well, then we would know how to solve it. And roughly how? I give you first a rough idea, and then we will do it in detail. Let the operators f hat evolve according to h hat is easy of t. By assumption, we can do this. And then try to solve for psi of t, which evolve according to the h hat difficult of t. And this will acquire an index here, d for Dirac, right? And that will be a Dirac. The point is that the operators evolve according to the easy part of the Hamiltonian, and the states evolve only according to the difficult part of the Hamiltonian. So let's see how this plays out exactly. So how? Well, Dirac's method is this. First of all, solve, and we assume that we can do this because we declared a certain part of the Hamiltonian to be easy. So first we solve for the time evolution operator for the easy part. IH bar d by dt of u hat easy of t equal to Schrodinger Hamiltonian of the easy part of t u hat e of t. Can do by assumption. Okay, but we actually need the full time evolution operator, of course. We actually need u hat of t. What good is u hat e of t to us? Let's see. What's the difference? Let's ask, what is the difference between u hat e of t and the full u hat of t? Well, for unitary operators, if we want to know how much they differ, we write down their product, actually. One we take the inverse of, and the other one we leave as it is. So we define the following operator, u hat prime of t, and we define it to be u hat e of t dagger. So this is the easy time evolution operator that we just calculated, and multiplied with the as yet unknown full time evolution operator u hat of t. Now, why is this measuring how much the full evolution that we really want and the easy evolution that we can calculate differ? Well, it quantifies the difference because imagine for a moment that there is no difficult part to the Hamiltonian. In that case, the full u hat is the u hat easy, right? But what does it mean for u hat prime? Well, if u hat is u hat easy, then we have here u hat easy dagger times u hat easy. Because it's unitary, it's going to be the identity. So this is would be equal to the identity, and therefore not much of a unitary, just the identity map, would be the identity if h is hat difficult is 0, right? Because then the easy evolution is the full evolution. All right, so now we know what we are up against. What we need to calculate is this. What we need to calculate is a u hat prime, because if we have it, in effect, we need to calculate that, right? We don't necessarily need to calculate it explicitly, but we need to find out what's in this u hat prime. All right, so how to proceed then? Well, let's proceed the same way, as far as we can, that we did with the Heisenberg picture and that we did with the Schrodinger picture. So we have that u hat of t is equal to what? Well, if we just solve this equation for u hat by multiplying from the left with the u hat easy, then we get formally an expression for the full time evolution operator, right? So we get that this is u hat easy of t times u hat prime of t, right? So we took this equation and we multiplied it from the left with u hat easy. And u hat easy times u hat easy dagger is just the identity. So we're left with u hat. And over here we had u hat easy times u hat prime. So that's what we have here, u hat easy, u hat prime. Now, how do we calculate predictions now? So calculate predictions as usual as f bar of t equal to psi u hat dagger of t, that's a full time evolution operator, f hat of t naught u hat of t. Remember, this is always true. This is not specific to any sorry, what is this bar doing? This is not specific to any picture. This is true in every picture. And then we choose a picture by choosing how we bracket this expression here, right? Also, let's keep in mind that while we have so far calculated this bit, or that bit we don't know yet. So in any case, formally, we can write that the observables, the observable predictions, are calculated as usual this way, but the U hat is now the product of two operators. So let's spell this out. You can write this as psi, and then the U hat dagger is the dagger of this. So it is U hat prime dagger of T, U hat easy dagger of T. Remember that if you take this product and you take the dagger of it, then you're daggering each component, each of the two factors, but you're also swapping their places. And then we have here F hat of T naught, and then U hat easy of T, U hat prime of T psi. Now, what do we gain by doing this? Well, what we have gained here is that we recognize a friend of ours. See, this thing here, we had given a name earlier. Actually, let me just put the bracket everywhere. So this thing is F hat of T in the Dirac picture, because remember, what we have done so far is that we have solved, by Dirac's method, we have solved for the time evolution operator of the easy problem, the easy Hamiltonian. And that means that we can now evolve the observables according to the easy Hamiltonian. And so in the Dirac picture, this is the observable evolved according to the easy Hamiltonian. Now, that suggests that this time-dependent vector shall be given the name psi of t d in the Dirac picture. And then that vector here is psi of t d, also in the Dirac picture. So what we then obtain is, so this is by definition here, right? Definition, by definition. Oh. Definitions. And so overall, we have that f bar of t. In the Dirac picture, we are calculating expectation values this way, psi of t in the Dirac picture, and then f hat, the Dirac picture of t, and then psi of t, again, Dirac picture. Where some parts of that we know how to calculate, some parts we haven't really figured out yet. So what we can calculate is this part, right? The f hat d of t, because by assumption, we can calculate the solution to this problem. For the easy Hamiltonian, we can calculate the easy time evolution operator, and the easy time evolution operator, just like in the Heisenberg picture, can evolve our operators. It's not the Heisenberg picture though, because our operators are not evolving according to the full Hamiltonian, but only according to the easy Hamiltonian. So this piece, by assumption, we can solve explicitly because it's obtained from just the easy part of the Hamiltonian. Now the question is, how can we calculate this psi of t? Now, of course, we can calculate this psi of t by calculating what u hat prime of t is. But that's back to square one, right? Because that's the missing unitary that would get us to the full unitary. No, hopefully there's a better method to get to psi of t directly without having to calculate u hat prime of t. And indeed, there is a method for that. Okay, so let's, before we get into that, let's take stock. So, in the Dirac picture, in the Dirac picture, what is the equation of motion for f hat d of t? Well, it's exactly like in the Heisenberg picture, except that we are using only the easy part of the Hamiltonian. So the answer is that f, oh, I need more space. The answer is that f hat d of t is equal to, well, time evolved, easy time evolution operator, dagger, f hat d of t naught, and u hat e of t. We could also write here that it is just f hat of t naught, right? So this is equal to f hat of t naught. And that means that the equation of motion is I h bar d by dt of f hat Dirac of t equal to, and then here we have f hat d of t, h hat easy d of t. And what is the Hamiltonian here? So here, h d e of t equal to the Hamiltonian with its operators evolving in the Heisenberg picture for the easy Hamiltonian. All right. But secondly, what is now the equation of motion for this state, for psi of t in the Dirac picture? That's the non-trivial part now. Now the answer to that is in a theorem. And the theorem simply says that IH bar d by dt of psi of t d, so the Dirac states, evolve according to a Schrodinger type equation of motion. But there is a lot to be said about it because it's not really a Schrodinger equation with initial condition that the Schrodinger, the Dirac state at t naught equal to psi, it's the Heisenberg state, the Heisenberg initial state, where, or here, we have that this Hamiltonian, the Hamiltonian in the Dirac picture, and that's a very important detail, that sometimes beginners forget, the Hamiltonian in this Schrodinger type equation for the Dirac states, the Hamiltonian is the difficult Hamiltonian right? That's why there is this superscript D, difficult Hamiltonian. But what are the operators in the Hamiltonian doing? Are they going to be frozen? Are they going to be evolving according to the full time evolution, to the full Hamiltonian? No, they're going to evolve. The operators inside that Hamiltonian are going to evolve according to the time evolution of just the easy Hamiltonian. So the Hamiltonian in the Dirac picture that evolves the Dirac states is the difficult Hamiltonian with its operators evolving according to the easy time evolution. U had easy of t. So this is what the theorem is claiming. And if it's right, what it means is that if we want to work in the Dirac picture, then we have to first solve the time evolution of the operators. Remember, the time evolution of the operators is according to the easy part of the Hamiltonian. And once we have that, we can plug the time evolved operators into our Hamiltonian. And that is going to be that Dirac Hamiltonian in the Dirac picture, the difficult Hamiltonian in the Dirac picture. So again, first step is that we solve the easy time evolution for the operators. And then we use that time evolution in the difficult part of the Hamiltonian and solve then this Schrodinger type equation. All right, we need to prove this. Proof is actually surprisingly long. Works like this. We know that the following is true, namely that I h bar d by dt of u hat of t is equal to Schrodinger Hamiltonian of t u hat of t. Remember, we could also write down the equation of motion for the time evolution operator in terms of the Heisenberg Hamiltonian, but the Heisenberg Hamiltonian would show up on the other side of the unitary there. All right, now remember that u hat of t is equal to u hat easy of t times u hat prime of t. Right? We had split the entire time evolution into these two factors. So therefore, what we have is that if we replace the u hat by these expressions, we obtain IH bar d by dt of u hat e of t, u hat prime of t equal to Schrodinger Hamiltonian. And then again, u hat easy of t, u hat prime of t. Let us spell this out further. So what we obtain is that IH bar, and then we have u hat e of t dot u hat prime of t plus I'm using the product rule here. You had easy of t, you had prime of t dot is equal to, well, and now let us write out the full Hamiltonian as the sum of the easy and the difficult part. So this is h hat easy part plus h hat difficult part, and then you had easy of t, you had prime of t. Now let's do a little side calculation here. Namely, let's do it in a different color. So, little side calculation. Namely, we have that IH bar d by dt, you had easy of t obeys, I mean, the easy time evolution operator obeys the time evolution operator's equation of motion for the easy Hamiltonian. H hat easy, showing a picture of t, u hat easy of t. All right. Now, let us multiply this equation from the right with the inverse of this. In this way, we get rid of this and we isolate the easy Hamiltonian. And that's nice, because then we obtain an expression for the easy Hamiltonian that we can plug into here. All right? Because after all, we want to get rid of this thing so that we are left with something that involves only the Hamiltonian, the difficult part of the Hamiltonian. So that, because remember where we are aiming at, we want to arrive at the Schrodinger equation, the kind of Schrodinger equation for Dirac picture states. So we want to get rid of this easy Hamiltonian. So we take this equation here, the defining equation for what u hat E was, and solve it now for the Hamiltonian. So therefore we have that IH bar and then u hat E of t dot, that's just what was written up there. And then we multiply from the right with u hat E of t inverse. So u hat E of t dagger, and this is the easy Hamiltonian of t. So we can plug that into what we have up here. So we can write therefore that this is equal to, just from up here, we have that the easy Hamiltonian is this, so it is IH bar u hat dot easy of t u hat easy of t dagger, and then we multiply, no, I'm writing now this term, right? So we multiply with u hat easy of t and u hat prime of t, where we notice that, how nice, this is equal to the identity operator, because that's the dagger of that, and the easy unitary here is unitary, so its dagger is its inverse. But now we also still have to add this term here, so we have on the right hand side also plus h hat difficult, showing a picture. Yeah, I mean, these two guys are time dependent. Oof, of t, so many decorations. Okay, so that's the difficult part. And then u hat E of t, u hat prime of t. Okay, so we need to read it this way, that this is the left-hand side and that here is the right-hand side. In fact, we can try this. We can try to copy this part, edit, copy, and write it down here. Paste. Nice. So we write it like this. Okay, so we have this. Now, let's compare the terms left and right. What do we see? We see in particular that we have here a u hat e dot times u hat prime. We've seen that before, namely here. See, this term actually matches that term because these two just collapse into the identity. So therefore, that goes away against this one. And therefore, the equation that we are left with is that IH bar u hat easy of t u hat dot prime of t is equal to difficult Schrodinger picture Hamiltonian, and then u hat easy of t u hat prime of t. How about moving this term, this, over here? Right? How do we do that? We just multiply with its inverse from the left. Both sides of the equation, we multiply with the inverse of this unitary from the left. So we obtain that IH bar, and then u hat dot prime of t is equal to u hat easy dagger of t, because that's the inverse, and then h hat, h hat difficult Schrodinger picture of t u hat easy of t u hat prime of t. Doesn't look easy, but actually things are simplifying now, because what we have is that this thing here is a time-evolved Hamiltonian. Let's look at what it really is. This is the Schrodinger Hamiltonian. Well, it's the difficult part of the Schrodinger Hamiltonian. And because we have the time evolution operator of the easy part to the left and to the right, it means that all the operators inside are being given time dependence, right? Because we can write this as, h hat difficult of, and then we have here u hat easy dagger of t, and then all of the x hat operators, there could be any number of them with certain labels, and then the u hat easy of t, comma, and then the same thing with the p hat operators of t. Oh, this is of t naught, because remember that originally the Schrodinger Hamiltonian has operators that are frozen at the initial time. And then here we also have p hat of t naught frozen in time, and then the u hat e of t. So what that means is that if we call this thing, if we call this the Dirac picture Hamiltonian, then the interpretation of it, or the description, the exact description of it, is as follows. This is same as the Schrodinger Hamiltonian. Sorry, it's a difficult part. Same as this, except its operators evolve according to the easy evolution. Right, as we discussed before. All right, so what is our equation looking like now? Well, where have we arrived? We arrived now at this. We arrived at I h bar d by dt of u hat prime of t. I'm just carrying forward what we have up here, is equal to the Hamiltonian, well, the difficult Hamiltonian in the Dirac picture, so its operators evolve according to the free evolution, acting on u hat prime of t. So this is starting to look a bit like a Schrodinger equation, but not quite yet. What we need to do is now have it act on the state. So then we have I h bar d by dt of u hat prime of t acting on some initial state is equal to h hat, difficult part, Dirac, t u hat prime of t psi. Now, remember, this combination we had given a name. Namely, these were the time-dependent Dirac picture states. So, and this too. So this is psi of t in the Dirac picture. So therefore, what we have is that I h bar d by dt psi of t d equal to h hat d d of t and then psi of t in the Dirac picture. This is what we set out to prove, namely that the states in the Dirac picture evolve according to the difficult Hamiltonian in a Schrodinger type equation. And the difficult Hamiltonian, you have to keep in mind, has operators that evolve according to the easy time evolution. All right, so that is completing the proof of the theorem. So the summary is then this, summary of the method. First, the method consists in solving I h bar f hat dot of t. These are the Dirac picture time evolving observables, is equal to f Dirac hat of t, and then it's the easy time, the easy Hamiltonian. This is just ordinary Heisenberg picture. Everything the same as in the Heisenberg picture, except that we are only using the easy part of the Hamiltonian. And then secondly, we solve, and this is usually the difficult part, but it's made a little bit easier by using the Dirac picture. So we solve this equation here, difficult part in the Dirac picture of t and then psi of t, this. And here operators evolve according to u hat easy of t, i.e. according to equation star, where this is equation star. And then finally, in the third step, predictions. Obtained this way. F bar of t equal to psi of t in the Dirac picture, and then the operator in the observable in the Dirac picture, and then psi of t Dirac picture. Right. What's the advantage then? Well, often the difficult part of the Hamiltonian is so difficult that we can't actually solve the problem entirely. We have to do it with perturbation theory. And then when you do perturbation theory, the number of terms that we have to work with easily gets out of hand as we go higher and higher in the Taylor expansion. Perturbation theory means that you do the one or the other kind of Taylor expansion. And it's very useful, therefore, to have to solve in the interaction picture the time evolution only for the difficult part of the Hamiltonian. We only have to do the perturbation theory for this Hamiltonian, and the entire free Hamiltonian is gone. It's already solved. It's already incorporated in the problem that we know the solution to this, namely by having put the time evolution, the free time evolution, into the way that the operators inside that Hamiltonian are evolving. So overall, that's usually much less effort than having to solve the whole thing over and over again. Okay, so this is as far as we got today. We have now covered the Heisenberg picture because that's what we did all along. And then we covered the Schrodinger picture, and today we did the Dirac picture. And there is one more picture to come up. Okay, see you then. Bye-bye.